Alrighty. Um, I added some of these websites for problem sets that I think I'll start doing at some point. I'm basically using this README as a dumping ground of all the things that I want to learn. So far, it's 77 lines, but it's split into like blogs that I want to read, talks I want to watch and take notes on, books I want to read, lots of books, documentation I want to read, courses I want to take, problem sets, and links off to my notes. So if I quit out of here, what was it called? Gulp, grip, something. Well, README. What was it called? Glow. If I use Glow on this thing. So the stuff that I'm actually working on has these notes sections where I link off to notes. So yeah. I'm going to just continue to add to this markdown file and then split off different repos for different projects that I'm working on. I ran across this one, getcracked.io. There's a guy on YouTube called Coding Jesus that created this website and has a lot of challenging problems on it, from what I can tell. C++, Rust, and Python, I believe. Click through here. Let's see. Content. Yeah, C++, Rust, and Python. And I have a lot of experience with Python, a little bit of experience with Rust, and a little bit of experience with C++. But I do have a Rust book that's on my queue that I would like to get through, a second Rust book. I already read the Rust programming language from the website, and yeah, so I got a pretty decent understanding of the language from going through all those exercises and everything. But I haven't implemented anything serious in Rust, so my experience with that is minimal. I probably implemented more stuff in C++, just because I used this during college and I actually did write some projects in it. But he goes into he's a C++ guy from what I can tell, and he goes into a lot of like niche things. Let's see, quizzes. But yeah, don't want to spend too much time on this right now. But that is something that I want to start taking on at some point. I think it would be appropriate. Where do we leave off here? So we're picking up on the C programming language K&R C. And we left off on this code here, which was for the low-level I/O read and write. So we're not going to get much out of this because it's all about Unixy stuff that we already are really well familiar with, but let's go ahead and continue reading. So we got this program here. It's a getCar program. You just read into a buffer and return a pointer into that buffer. Let's go ahead and read through it. So integer, getCar void. So integer, this is a simple buffered version of getCar. getCar is a get character, but it's returning an integer. It's odd that they use integer. Integer is, on most systems, 32 and 64-bit. It's 32-bit wide, and a character is 8 bits wide, from what I remember. Let's jump over to K&R, and we're going to just LT here, and it was under, what, test int sizes? Yeah, chapter 1. Build test int sizes. So char is indeed 1 byte. I think it's assigned 1 byte by default. But you say get char and then you return integer. That's interesting. And then at the end here, you're returning a pointer dereference of buff p, and buff p is a char. So I'm not sure why you even go with the integer on that one, but maybe it's to allow for signaling somehow. I don't know. But there's a lot of bytes in an integer, as you can see here. 4 bytes. This is on 64-bit machine, but if I run it on 32-bit, which I have a 32-bit version of it, it's also 4 bytes. I think they did that with compatibility. I think previous versions of ints were Like a 16-bit architecture would have a 16-bit int, from what I remember. All right, so let's continue reading. So we allocate our stack memory here. So you just say char star static. Oh, these are static. Okay, even worse. So statically allocated automatic variables here persist, and they cause a lot of issues with the reentrancy and concurrent access and stuff. So not a great choice to use static memory generally. So let's go and continue reading here. So we have a buff size, we allocate a buffer, we get a pointer into that buffer, which is at the 0th element. It's character, so it's byte buffer. And then we have an int n, which is initialized to 0. We say, hey, if n is equal to 0, which it will be initially, we read from standard n, which is a 0 here, standard n. Even though there's a symbol for that, or a pound defined for it, you're just going to say 0 there, and then buffer is the address of where we're reading from, and then the size of buffer is the amount of size that we're reading into the buffer. And then we assign that to n, and then we say, hey, buff p is now equal to buff. I'm not sure what is changing there. I don't think anything changes there. I'm not sure about this line here. I have to come back to that. And then we just read from the buffer. So in the future, when n is not equal to 0, we skip over that stuff, and we just decrement n, and we increment. Okay, this is where we increment the buff p. So we say we're going to decrement n, and if it's greater than or equal to 0, if the character is greater than or equal to 0, then we're going to take that character. Otherwise, we're going to return EOF, which is actually a negative value. EOF from the read syscall is 0. So if it is indeed 0, then we return a negative value here. Otherwise, we take the unsigned char of the dereference of buff p, and then once we have that, we then increment the buff p pointer, as a second step. So what's getting returned here is the dereference of buff p cast as unsigned char, then also cast as an int as it's coming out. And then the buff p here assignment says, like, okay, our buff p has been advancing into the buffer. We've been decrementing n, so it's kind of weird. We fill the buffer, then we set the buff p to the root, and then we increment the pointer and we decrement n. So n is really the length of bytes that we have remaining in the buffer to read. And then once that hits 0, we then reset. We do another read and we reset our buffer back to 0, our buff p back to 0. So we're just filling a buffer, reading from it. N is going down, and once we've read everything from the buffer, we then do another read. If these versions of getcar were to be compiled with standard IO included, it would be necessary to undefine the name getcar in case it is implemented as a macro. Okay. So we got open, create, close, and create, close, and unlink. Other than the default standard input, output, and error, you must explicitly open files in order to read and write them. There are two system calls for this, open and create. I wasn't familiar with create. Let's do man syscalls, create. Oh, interesting. Man to create. Oh, interesting. I knew about open and open at, and I guess open at too, but I didn't know about create. I guess because usually you do an open create instead of creating a file. But yeah, it's very similar to the open with the create, just without the flags. Okay, I guess I did learn something here, because create is not very popular. A call to create is equivalent to calling open with flags equal to create, write only, and trunc. Okay, create, write only, and truncate. What if you want to read from it though? Yeah, that's why I prefer to like not use that and just use open and specify the flags that I want. But good to know that that exists. Open is rather like the fopen discussed in chapter 7, except that instead of returning a file pointer, it returns a file descriptor, which is just an int. Open returns -1 if any error occurs. Int fcntl, got a file descriptor, say open, char star path, and the flags and the permissions. That's just a forward declaration, and then we actually call it. As with fopen, the name argument is a character string containing the file name. The second argument, flags, is an int that specifies how the file is to be opened. The main values are read only, open for reading only, write only, read write. These constants are defined in fcntl on system v Unix systems and in sysfile on Berkeley BSD versions. I'm only familiar with the fcntl header. To open an existing file for reading, you say, hey, I'm going to open read only, and I don't need to give it any. I think you can even just ignore, like not even include the mask or permissions. Sorry, permissions, because you're not going to be creating this file if you're doing read only. There's no ocreat here, so I think let's go and test that. Test.c pound include fcntl.h main up, and we'll do standard lib, and then here I'm say open. We'll just say foo. All right, so we got open foo. And we'll say rd only. Yeah. And then we're not going to give it permissions. We're going to get back fd, which we'll assign to an int, and we'll just print out our fd, assuming it's not an error. If it is an error, we'll know because it'll be a negative value. fd, bam. So this might actually fail. Oops. fcntl, and then we need standard IO because of the printf. Cool. So now if we do make on this, build test, test, and say -1 because foo doesn't exist. So if I touch foo and run it, yeah, exactly. rm test.c. So before I do that, so it just proves that you don't actually need to give the permissions as a third argument. rm test.c, make clean. Let's get out of there. Okay. Boop, 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 boop. Next page. Boom. The perms argument. Okay. The perms argument is always 0 for uses of open that we will discuss. It is an error to try to open a file that doesn't exist. The system call creat is provided to create new files or to rewrite old ones. Okay, return a file descriptor if it was able to create the file, and -1 if not. If the file exists, creat will truncate it to 0 length, thereby discarding its previous contents. It is not an error to create a file that already exists if it truncates it though. If the file does not already exist, creates it with the permission specified in the perms argument. In the Unix file system, there are 9 bits of permission information associated with the file that control read, write, and execute access for the owner of the file, for the owner's group, and for all others. Thus, a 3-digit octal number is convenient for specifying the permissions. For example, 0755 specifies read, write, and execute permissions for the owner, and read and execute permissions for the group and everyone else. To illustrate, here is a simplified version of the Unix program CP, which copies one file to the other. Our version copies only one file. It does not permit the second argument to be a directory, and it invents permissions instead of copying them. I don't really care about their toy copy program, so I'm going to skip on from that. This program creates the output file with permissions of 0666 with the stat system call described in section 8 6, we can determine the mode of an existing file and thus give it the same mode to the copy. Notice that the function error is called, well, maybe go back. Let's go and review it. So we got our void error char star variadic arguments. It's pound including the syscalls.h, which is not a real thing. Define perms as 666. Okay, and we take in our 2 arguments. We just do an error to make sure there's at least 2 arguments provided to the program. We then open F1 for read only. We create, which is going to truncate, which is fine, I guess. With perms. And then while we read from F1 buffer, we then write F2 the buffer, and then we return 0. So while there is data to be read, we're going to write the data to it. And if it doesn't perform a write that's the same size as the read, then we're going to error out. Which really, you should have a nested loop here, because you could just do, I'm pretty sure the kernel could possibly say, okay, you wanted to write n bytes. I wrote, n divided by 2. And so you have to perform 2 writes for the 1 read. And that should be fine. You should just handle that case. I don't know why they're making the assumption that the write has to be the same size as the read. Maybe there's something that I'm aware of where it guarantees that. But yeah, let's go through. Where are they talking about copying the permissions? It looks like they're setting it to 0666. And there's no statting here, so I don't know what they're talking about. This program creates the output file with fixed permissions with the stat. Okay, they're saying if you wanted to, the stat system call described in section 8.6 we can determine the mode of an existing file and thus give it the same mode to a copy. Okay. Notice that the function error is called with a variable argument list, much like printf. The implementation of error illustrates how to use another member of the printf family. The standard library function vprintf is like printf, except that the variable argument list is replaced by a single argument that has to be initialized by calling the va start macro. Similarly, vfprintf and vsprintf match fprintf and sprintf. Okay, so we're gonna do variadic argument stuff here, where we just grab everything. We say, okay, this is va list args. We start after the format argument. We print out error colon. We then do vprintf, where we give it the format and the args. And then we throw a new line to standard error. This is all going to standard error. And then we say van to make sure that args is cleaned up, because the args itself is on the stack here, but it might point to things that are on the heap, I guess. Okay, there is a limit, often about 20, on the number of files that a program may have open simultaneously. Definitely not that small these days. Accordingly, any program that intends to process many files must be prepared to reuse file descriptors. The function close fd breaks the connection between a file descriptor and an open file and frees the file descriptor for use with some other file. It corresponds to fclose in the standard library, except that there is no buffer to flush. Termination of a program via exit or return from the main program closes all open files. Technically, it closes all open file descriptors. Nowadays, at least. The function unlink char star name removes a file name from the file system. It corresponds to standard library function remove. Exercise 8.1, rewrite the program cat from chapter 7 using read, write, open, close instead of their standard library equivalents. Perform experiments to determine the relative speeds. I don't care about that. Random access lseek. Input and output are normally sequential. Each read and write takes place at a position of the file right after the previous one. When necessary, however, the file can be read or written in arbitrary order. The system called lseek provides a way to move around in a file without reading or writing any data. Okay, so we got our long lseek int fd, long offset int origin. and returns a long. Okay. So that function sets the current position in the file whose descriptor is FD to offset, which is taken relative to the location. Give me 1 second. Sorry, I need to make sure that I log my calories this morning. I ate breakfast and forgot to log them. It's gonna just nag at me if I don't do it. Mangoes, add some mango. Protein shake. Some mixed nuts. Boom. Okay. Alrighty. So anyways, lseek sets the current position of the file whose descriptor FD to offset, which is taken relative to the location specified by origin. Origin could be one of 3 things, I think. Subsequent reading and writing will begin at that position. Origin can be 0, 1, or 2 to specify that offset is to be measured from the beginning, from the current position, or from the end of the file, respectively. For example, to append to a file, the redirection greater than in the Unix shell, or A for fopen, we seek to the end before writing. I think you'd want to open in append mode, though. That would probably be more equivalent. Because when you lseek to the end, for a single-threaded situation, it's fine. But I think with the append mode, if you have multiple file descriptions pointing to the same file, and it's in append mode, and you have multiple writers to those file descriptors, like say you had 2 separate processes entirely, they have 2 separate file descriptors, they have 2 separate file descriptions, and they're pointing to the same inode for the file, and they're performing writes. Their lseek offset, like their offset into the file, is not going to be coordinated. Whereas if you open them in append mode, it will be. Like you won't write over each other. I think that's the difference there. So you'd really want to use the append flag when you're opening the file versus doing an lseek in the situation. To get back to the beginning, rewind, you go to 0. Notice 0L argument, it could be written as a long 0 or just as 0 if lseek is properly declared. With lseek, it is possible to treat files more or less like large arrays at the price of slower access. For example, the following function reads any number of bytes from an arbitrary place in a file. It returns the number read or -1 on error. So we say, hey, get from this FD at this position in this buffer where we're going to write it, this many bytes. So we lseek to that position, and then we do our read into the buffer for that many bytes. Yep. The return value from lseek is a long that gives the new position in the file, or -1 if an error occurs. Standard library function fseek is similar to lseek, except that the first argument is a file star, and the return is a non-zero if an error occurred. Example, an implementation of fopen and getc. Let us illustrate how some of these pieces fit together by showing an implementation of standard library between fopen and getc. Recall that the files in standard library are described by file pointers rather than file descriptors. A file pointer is a pointer to a structure that contains several pieces of information about the file. A pointer to a buffer so that the file can read large chunks, a count of the number of characters left in the buffer, a pointer to the next character position in the buffer, the file descriptor, and flags describing read-write mode, error status, etc. There's a lot of stuff in the fopen file type. I looked at it briefly a couple weeks ago, and there's just a lot of stuff there. I mean, we can do it right now. We can just do like a vim test.c, and we're going to go like pound include, and we'll do, standard io.h, and we'll say, hey, file, what is this? Okay, Maybe we have to declare a file pointer foo. There we go. Has to be valid syntax. There we go. So that is a type def to this thing called struct IO file, which is of course not helpful here at all. So we're going to file.h. I want to go to standard IO. I thought it was in here. File. Okay. Struct file. Let's see if I can find it. I thought I found this thing before. Let's go to the bottom, go up. Let's go to definition on that. No. Okay. They're all going to this file.h. I want to go to underscore file.h. That's just to type if def it. But the struct file, here we go. Yeah, and this is going to be, so this thing goes to IO file, which has a for declaration here as just a struct. But then if you go here, IO file is again redefined here, but that's just a for declaration. This is the actual definition. So these are all the things that are in the file struct, which is a lot more than just a few things. The tag name of this struct is underscore IO file to preserve historic C++ mangled names for functions taking file star arguments. That name should not be used in new code. Okay, so you got higher order word is IO magic, resets flags. Now, I'm not going to go through this. I just wanted to illustrate that there's a lot of stuff in here. And it's chained as well, Jesus Christ. So you can have pointers to it inside of it. So we're not going to look into that further. I just wanted to illustrate that, that there's a lot there. All right, let's continue reading on their implementation here. So the data structure that describes a file contained in standard io.h, which must be included by #include. In a source file that uses routines from standard input-output library, it also include by functions in that library. And the following excerpts from a typical standard io.h, names that are intended for use only by functions of the library begin with an underscore. So they are less likely to collide with names in the user's program. This convention is used by all standard library routines. So we got our code here, a bunch of pound defines. Okay. Let's start from the top. So we just got null EOF buff size and open max. Then we type def up a struct called file. So this is a much simpler version. And the struct is called IO buff. It has how many characters are left, a pointer to the next character position, location of the buffer itself, flag for the mode of file access, and the file descriptor itself. So I guess the buffer is allocated on the heap. And then we create this file IOB open max. So we just have these structs already pre-allocated. Let's see. Then we define our standard in, standard out, and standard error as indices into that and a reference to it. Okay. So say, hey, IOB, grab your 0th element. So instead of copying the struct, which is what that would do if you didn't have the reference, it takes a reference to it, which is right because all the standard library file IO functions take a pointer. So that's completely right there. And then we got enum underscore flags. We got read, write, buff, EOF, and error as flags. So it's 1, 2, 4. I wonder why they did 10 instead of 8. 1, 2, 4, 10, 20. And then we fill buff file, flush buff, int file. Then we pound define EOF, FEOF, F error, F file no. Huh. Get C, put C, get char, put char. Okay. So these are just macros on top of the file struct. The get C macro normally decrements the count, advances the pointer, and returns the character. Recall that long pound define. Sorry, next page. Recall that long pound define is continued with a backslash. If the count goes negative, however, the get C calls the function fill buff to replenish the buffer, reinitialize the character the structure contents, and return the character. The characters are returned unsigned, which ensures that all characters will be positive. Although we will not discuss any details, we have included the definition of putC to show that it operates in much the same way as getC, calling the function flush buff when the buffer is full. We have also included macros for accessing the error and end of file status and the file descriptor. Function fopen can now be written. Most of fopen is concerned with getting the file opened and positioned at the right place and setting the file flag bits to indicate the proper state. Fopen does not allocate any buffer space. This is done by fill buff when the file is first read. Don't really care about this stuff, so I'm going to skip over that. It's just going to be more of the same. This version of fopen does not handle all of the access mode possibilities of the standard, though adding them would not take much code. In particular, our fopen does not recognize the B that signals binary access. I've never used that in my entire life. I know what it is, but bytes are bytes, whether they're binary or characters, doesn't matter. Since that is meaningless on Unix systems or the plus that permits both reading and writing, the first call to get C for a particular file finds the count of 0, which forces the call of fill buff. If fill buff finds that the file is not open for reading, it returns the OF immediately. Otherwise, it tries to allocate a buffer if reading is to be unbuffered. Once the buffer is established, fill buff calls read to fill it, sets the count and pointers, and returns the character at the beginning of the buffer. Subsequent calls to fill buff will fill a buffer allocated. Don't care about any of this. So we have a couple pages on directories, which I might just blast through that because I don't really care about directories either. We're trying to get to the storage allocator part because that's the part that I actually think would be interesting. But for the sake of completion, I just want to at least read the text here. I don't necessarily need to read the code for all this. Okay, the only remaining loose end is how everything gets started. The array IOB must be defined and initialized for standard in, standard out, standard error. Don't care. Initialization of the flag part and the structure shown in standard in is to be read, standard out is to be written, standard error is to be written unbuffered. Example A2, rewrite fopen and fill buff with the fields instead of explicit bit operations. Compare code size and execution speed. Do not care about that. Exercise 8.3, design and write flush buff, flush, and fclose. Don't care about that. The standard library function fseek. Don't care about that. It's identical to lseek, except that fp is a file pointer instead of a file descriptor. And the return value is an int status, not a position. Write fseek. Make sure that your fseek coordinates properly with the buffering done for the other functions of the library. Example listing directories. So let's dive into this stuff. I'm just going to blast through it. A different kind of file system interaction is sometimes called for determining information about a file. Actually, before I go too far into this, I did want to highlight this one thing I learned in this chapter. I'm trying to get good at going back and highlighting things that I learned. And that was the create system call. I feel like I might have run across it before, but just so uncommon that it wasn't fresh in my mind. All right, so listing directories. A different kind of file system interaction is sometimes called for determining information about a file, not what it contains. A directory listing program such as the Unix command ls is an example. It prints the names of files in a directory and optionally other information such as sizes, permissions, and so on. The ms-dos dir command is analogous. Since the Unix directory is just a file, okay. ls need only read it to retrieve the file names. I don't think that is the way you do it anymore. Damn it. Let's go back here. Zoom out a little bit more here. So if you man up syscalls, there is reader syscall now. That's the way that they want you to do it. I wonder what happens when you read from a directory though. Let's do that. Vim test.c pound include. I'm just gonna say standard io.h standard lib. We'll main here. Main. And we're going to open our path to dir, and we're going to give it read only, and we're not going to give it the bits. We need to do fcntl here, fcntl, and then we get back our fd as a integer, because open gives back an integer, I believe. Yep. And then we say if fd is not greater than or equal to 0. It should really be greater than or equal to 3. Something like that. I guess I can just do like less than, right? That'd be silly. If it's less than 3, then we got an error, p error, out, open. And we'll just return exits failure. So now we have our, actually, you know what? I'm just gonna do assertions here. Let's grab our assert.h. And here we're going to say assert that's greater than or equal to 3. Okay. And then once you have it open, I'm just going to do a read on fd into the buff. So a buff is going to be a char array of, we'll do 4096. We'll read into buff. Size of buff, and we get back n, and we say assert that n is greater than or equal to 0. This needs to be declared. I'm going to start using auto, because why not? I want to start writing a little bit more modern C. Vim make is there not a make file here? Okay. Dash iname dot clang d. Well, let's just not worry about it for now. We'll just say int. I do want to start using more modern stuff. Read, I thought you would get that from fcntl, but let's just go man to read. It is in Unix standard.h. Unix standard.h. Okay, so we performed our read. We say if n, or we can say just like printf buff is equal to %s. I'll throw a new line there. Here's going to be buff, but we're going to say only read up to a certain number of bytes. So that means that buff sub n is going to equal to /0. So that'll terminate the string. And then we just print it all out. It's probably going to be some binary shit. We don't care about the error code there. Okay. GCC test.c a.out. So it wasn't able to get the file descriptor, but if I mkdir dir, and then I do it. Okay. I guess let's get a little bit more helpful. Let's take away the assertions. That was a bad idea. Because I do want to know what the error no value was. So if FD is less than 3, no, yeah, P error out from the open and return our exit failure. And then here, so if it is, so we're testing for greater than or equal to 0. So if it's less than 0, if n is less than 0, we're going to P error out the read and then exit. All right, make or GCC a.out. So you can't open it, you can't read from it. So if I rmdir on dir, and then I run it, but then if I mkdir dir and then run it, it says read is a directory. Would say in K and RC, they say you can read from dir a directory as you would a file. However, I was was under the impression that you had to use read dir. Was it man to read dir? Syscall. I tested it and read on a directory gave me the error no for we'll do here so we can say something like, why is this? My guess is that read dir is the only way that you can do it. Unix systems directory was literally just a file containing a sequence of directory entries. You could open it and read from it and manually parse the raw directory entries. Directories were special formatted files in the file system. No read dir existed yet. Modern Unix POSIX behavior. Read on a directory fails, you get E as dir. You must use open dir, read dir, close dir. These wrap the underlying getDents and getDent64 system calls, get directory entries. Why changed? Because allowing raw read exposed file system internals was not portable across file systems. Made format changes ABI breaking, because people would assume that there's specific ABI. With directories was unsafe and fragile. Modern systems force abstraction. Directories are not readable as byte streams. What actually happens on Linux internally, reader calls getDent64, which returns a packed structure of dirent 64s, but is not the same as reading raw file system blocks. Why K&R says this? Because K&R first edition reflects version 7 Unix directories were literally files you could read. Read dir came later with BSD POSIX standardization, so the book is historically accurate but not reflective of modern POSIX systems. Given that, I'm going to rm a.out and test.c, and we're just going to in rmdir dir, we're going to just skim through this because I'm guessing that it's going to do some silly stuff here. No, it uses open dir read, but it uses these functions that we defined, open dir and read dir. I don't see them. Yeah, these are using their own dirents. I mean, it might be interesting to read it just for the historical context, but this is like old, so old that it's no longer relevant at all. But I'm going to go ahead and blast through it just to get some historical context. So different kind of file system interaction, sometimes called for determining the information about a file, not what it contains. A directory listing such programs such as Unix command ls, an example, it prints the names of files and directories, and optionally other information such as sizes, permissions, and so on. MS-DOS dir command is analogous since the Unix directory is just a file. ls needs only read it to retrieve the file names. So that's not true. But it is necessary to use a system call to access other information about a file, such as its size. On other systems, a system call may be needed even to access file names. This is the case on MS-DOS, for instance. What we want to provide access to the information in a relatively system-independent way, even though the implementation may be highly system-dependent. We will illustrate some of this by writing a program called fsize. Fsize is a special form of ls that prints the size of all files named in its command line arguments. If one of the files is a directory, fsize applies itself recursively to that directory. If there are no arguments at all, it processes the current directory. Let's begin with a short review of Unix file system structure. A directory is a file that contains a list of file names and some indication of where they are located. Location is an index into another table called an inode list. The inode for the file is where all information about the file except its name is kept. A directory entry generally consists of only two items, the file name and an inode number. Regrettably, the format and precise contents of a directory tree are not the same on all versions of the system. So we will divide this task into two pieces and try to isolate the non-portable parts. The outer level defines a structure called the dirent, and three routines: open dir, read dir, close dir, to provide system-independent access to the name and inode number in a directory entry. We will write fsize with this interface. Then we will show how to implement these on systems that are the same structure as version 7 and system V Unix. Variants are left as exercises. The direct structure contains the inode number and the name, the maximum length of the file name component. I feel like all of this is just so pointless. Let's just skip this because it's just so wrong and dated that it's just like gonna be torturous just to read it. So I'm just going to skip that, and we're going to go to storage allocator. All right, so this is a 4-page section here, and there's a good section, maybe a page of code. So this is something that I'm actually interested in working on here. So I'm going to mkdir chapter 08. cd, actually, let's do our find make file. So we're going to copy from chapter 06 our files for make.dir and make file and .git ignore into chapter 08, and then and then we're going to cd into that directory, and we're good to go. In chapter 5, we presented a very limited very limited stack-oriented storage allocator. The version that we will now write is unrestricted. Calls to malloc and free may occur in any order. Malloc calls upon the operating system to obtain more memory as necessary. These routines illustrate some of the considerations involved in writing machine-dependent code in a relatively machine-independent way, and also show a real-life application for structures, unions, and typedef. Rather than allocating from a compiled fixed-size array, malloc will request space from the operating system as needed. Since other activities in the program may also request space without calling this allocator, the space the malloc manages may not be contiguous. Thus, its free storage is kept as a list of free blocks. Each block contains a size, a pointer to the next block, and the space itself. The blocks are kept in order of increasing storage address, and the last block, highest address, points to the first. Okay, are we going to be using malloc? Probably not. Or sorry, are we going to be using mmap? Probably not. So what is the... How do they allocate here? Yeah, they use the S break system call instead of mmap, which is to be expected. Okay. Should be interesting. So this is the memory. So the S break system call, let's go ahead and just review that real fast. Man to S break. So break and S break change the data segment size. So that's basically the low address numbers of the what they call the break, which is the point at which stuff is being stored. At the bottom of the address space, I conceptually visualize it at the bottom. So break, you just set it to whatever address you want. S break is you give it an increment. So feature test macro requirements for glibc. I don't care about any of that. Description: break and S break change the location of the program break, which defines the end of the process data segment. I.e., the program break is the first location after the end of the uninitialized data segment. Increasing the program break has the effect of allocating memory to the process. Decreasing the break deallocates memory. Break sets the end of... I wonder if we can set it to -1. Vim test negative sberk.c main pound include standard lib.h, and then if we man to sbreak, it's going to be in Unix standard.h. Unix standard.h. Here we're going to say, hey, I want you to sberk an increment of -1 and see what that does. That gives us back a void star p. I'm going to do auto here, auto p, and then we're just going to say, hey, printf out the p is equal to %p new line, give it p here. We need standard IO now, and then we're good. And then we need to go here. Where did I do this Clang-D thing? Was that in... That was in the Linux program interface. Find iname.clang-d cp chapter 09 /.clang-d. Actually, I'm just going to cat that out into Wayland copy, cd back to my thing here, Wayland paste into .clang-d, vim that up here. I don't care about any of these, but I do care about std equals 23. I think that's how you do it. Now when I write this, is it C23? Sorry. Go away, please. Jobs. Foreground. Please quit. Clang-D C23? That's how you do it. Vim test. Okay. Wait a minute. sbreak is part of uni standard.h. Uni standard.h. But I probably need some type of like... You say default source. Pound define default source. There we go. So that gives us our sbreak back. All right, so now we can make. No, we can't make because our make file needs to have stood is equal to C23 like that. Make. There we go. Build. Okay. That seems like a very high address. I wonder what happens when we set our break to 0. So our break is going to be where we have uninitialized data, right? So maybe we say int foo. Or maybe we'll do a big byte array. Char foo array of 2, or we say 1 bit shift over 8. How many is that? Python 1 bit shift over 8, 256. So we want to go maybe 20, which is 1 meg. 20. Okay. And then here we're going to say printf of foo sub 0 %c new line foo sub 0. So I'm going to do this before the break and then after the break reset, and then we'll do it again here. Negative, we'll do negative on 1 to the bit shift over 20. Do it like that. Make. Make. And instead of doing C, I'm just going to do D. So I can actually see what it is. It should be a 0, but just want to make sure. Yeah. Make file, oops, sorry. Vim test. So now I'm going to do a break, not an S break, man to break. And I'm just going to set it to 0 because why not? 0. And this is back an error auto. If error, sorry, error is less than, well, let's just look at return. So it's not equal to 0, -1. Error is less than 0. And we p error out. Say Burke gave us an error. Return exit failure. Otherwise, we print out this guy here. Okay, there's no problem doing that. And then maybe if we go and try to do another S break here. Of -1, make, that should blow up. How does that, and then it's not even set correctly. So I'm going to start off with doing an S break of 0. Okay. And then we did a -1 and it went up? How is that even possible? No, we did our... Yeah, let me just print out what we're doing. Printf sbrk of 0. New line. And then here we'll say sbrk of -1. And then here we'll say sbrk of -1 to the power of 20. And then here's a break of 0. And then here's another sbrk of -1. And then I want to do a break. I want to get this thing to fail. Basically, that's what I'm trying to do here. Let's do a break of -1. -1's invalid address. So what did I want to do here? Break of like 5. And then sbrk of -1. Trying to group these together a little bit. Do sbrk of -1 from 0. We'll just call this thing a void star. Make. How did none of this blow up? And it's not even setting the... So these are like you're asking the kernel to do something, and whether it does it or not is like up to it. So setting break to 0 or calling sbrk 0, increment of 0, just returns the current value. Everything's happy. Saying -1, it's like, yeah, I'm not going to do that. Go screw yourself. And then calling sbrk on some large number does in fact move it back, but not by much. It just gave you back by -1. Bizarre, absolutely bizarre. That's what I would expect it here, but it shows up when we do this thing. Okay, and then we say, hey, just set your break to 0, and I'm sbrk -1. Didn't change it at all. I'm going to say, hey, just set your break to 5, and then sbrk -1. And it changed it by -1. Okay, so let's read the man page to see what's going on here, because some weird stuff. Okay. Break and sbrk change the location of the program break, which defines the end of the process data segment. I.e., the program break is the first location after the end of the uninitialized data segment. Increasing the program break has the effect of allocating memory to the process. Decreasing the break deallocates memory. Break sets the end of the data segment to the value specified by adder when the value is reasonable. It's like, when it's reasonable, we'll do it. The system has enough memory and the process does not exceed its maximum data size. It says if it's going up, but also if it's going down. It's like, I'm just going to not do that. sbrk increments the program's data space by increment bytes. Calling sbrk with an increment of 0 can be used to find the current location of the program break. On success, break returns 0. And error no sets. On success, sbrk returns the previous program break. If the break was increased, then this value is a pointer to the start of the newly allocated memory. Okay, that's why it's one off. On error, void star -1 is returned. Okay. So that explains why we see what we see. So let's go back here, add some clarity to this program now that we understand it a little bit better. Vim test. So up here we call sbrk 0, which just reads, which is great. Here we call sbrk -1. We print out the pointer value. But what we really want to say is that's the previous pointer value. So what we want to do is say CP. Call it CP. Okay. So here we'll have CP and CP, and we'll set them like this, even though we call them like that. I'll do it like that. So here, whatever, we'll do it like this. Makes it a little bit easier. Here we go. All right, so we do S break 0, which just reads their current value at 8,000. Then we call S break -1, which will a previous value is 8,000. We actually do go by -1. So that explains why we saw like a offset in our calls. And then we call this like S break -1 million, basically, in which case our previous value is going to match, but our new value matches, which basically means that it didn't care about our call. It's like, okay, it doesn't matter. We're not gonna do that. And then if we call break 0, it didn't do anything. And then if we call S break -1, it does do something. It decrements it by -1. And then break 5. Maybe instead of doing 1,000,000, we do like 1,000. Break 5 doesn't do anything. S break -1 does do something. So we're able to reduce it by 1, but not by 1,000,000. Let's go ahead and, instead of doing this expression here, negative, what do we want to do? 4096 maybe? Make okay, that did something. And instead of grabbing 0, in addition to grabbing 0, I'm going to grab size of foo -1 here. We'll just call it -1 here. At some point, I anticipate this being like unreadable memory, because we like yield it back to the operating system, right? New line here. Just want to space these out a little bit so it's clear what's going on. Oops. Okay, should be everything. Make. Okay. I do need to upgrade or update the expression that I had. Where is it? This one here. This is -4096. Like that. And then I want to get my pointers to line up, so let's just add wherever we have quote P. I'm going to go next a space. There we go. Okay, so now our pointers line up so you can easily diff them. So this one definitely had an effect. This one definitely had an effect. This had no effect. This one had an effect. This had no effect. This had effect. And each time we're able to read from that -1 value. So I'm going to push this to the limits a little bit. And we're going to do this in a loop. So we say for auto I is equal to 0, I is less than 2000, I plus plus. And we're going to just do this in a loop. Make, run. Okay, I was able to do that no problem. But at some point it stopped readjusting the brake downwards. So I think what happens is it'll go down to a certain level and then it won't go down any further. So that's 63FF. So there's probably some address space layout randomization going on here, which is why these numbers are changing. But the vibe I get is that like it will decrease it down to a certain level, and then beyond that it will not decrease it. Actually, so these things are going down 7FF, not changing anymore. And we get here -1, it does go down 1. That I didn't want to see that. What are we doing here? CD, go back. Get status. Cat chapter 1 foo? What is that? RM that. Get status, get at all. Alright. Make. Foreground. Vim. Test. There we go. So let's bring this down to 1. And we'll do 2 million here. Okay. Well, let's fix this to be -1 as well, so that we're So we got a segmentation fault after S break. S break -1. We didn't even get a chance to print out our pointers. That means that S break -1 caused a segmentation fault, which is amazing. Oh no, it was this here. Let's reorder these. Yeah, these really should go in the order that they're being assigned into. Instead of the printf order. So it'd be more like this. There we go. CP, CPP, CPP, CP, CPP, CP, CPP, like that. Fascinating. The S break itself segmentation faulted. Let's print out I along with all this stuff so we know how many bytes we're going on here. Well, okay. Printf. We'll say, hey, I is equal to %the new line. Give it I and a semicolon, and we're good. Now I'm just going to say up here what this program is intended for. This program is intended to push the limits of break and S break, see how it behaves when we are freeing memory that is used by freeing memory in the data segment that is in use by the program. Something like that. Make run. So we got to 135166, 135166, 135166. Why does it segmentation fault after the S break? I wouldn't think it would do that. Negative S break can't invalidate existing memory. Let's cat out our test into or just do that, and then also grab. Well. Oh, let's go ahead and rewrite this to use. Right, that's a good call. Printf of A, sorry, pound define. Sorry, char outbuff 255. This would be a buff stir len of A. There's right hex, right int, right char, right stir. So I'm going to right stir. Hmm. That's not going down at all. Head. Yeah, it's not going down at all. Hmm. Why is it not going down at all now? My previous test program. I guess it did accesses along the way. Let's do one of these. Here we go. And we'll say adder foo sub 0. And it's literally just going to be this. And then we'll do adder foo -1. I think I can, yeah, that should be fine. Sorry, I need to say ampersand. Because that'll give me, accessing this will give me back the value 0. So I want the reference to that location. And then same thing here. I'm going to print out the hex here. I want to have that. Alright, make. So it goes to, oh wait, we gotta space these out a little bit more. Okay, so that means that 2 on that one and then 1 on the rest. Okay, so that means you need 1, 2, and then you just need 1. Oops. And then you need 1, 1, 1. Okay, so this is well below the break. The break is not coming down. So I think the reason we saw the break changing before is that we were using printf to malloc. And then lowering the break. So as long as we're not using like printf, which is increasing the break, and then we're lowering the break at the same time, we're not going to get a segmentation violation. Okay, so we have all this stuff that we're doing. Down here, I just want to capture this value, which is CP. Oh, we already have it captured. So we're going to say printf attempting to break CP minus 100. New line. Then here, and then we're not going to print that, we're going to write stir. If we look at the implementation for write stir, it has to have some, yeah, size t len. Okay, it just reads character at a time. It doesn't actually allocate space. Makes sense. Okay, so we're going to attempt to break. So here we call Burke of CP minus 100. Int error, and we say if error is not equal to nil, go, stuck in my brain. If error is less than 0, then we p error out saying Burke, and we return exit failure. Otherwise we do exit success. Okay, we'll do one of those. Oops. Okay. Sorry, vim test. We're gonna grab this read of CP. So I'll say old break here. No, this one here. Let that run. Yep, it just won't go down below that level. Cool. So we learned some stuff that, the operating system is sensible. It does sensible things. We also learned about how much allocation is going on when you do printf. It's quite a lot. I don't blame them. Printf is like pretty advanced because it uses like format specifiers and all that stuff. But yeah, the operating system, if you try to decrement sbreak below a certain threshold, it just silently fails and doesn't decrement. It's like, okay, I took your suggestion, but I'm not going to do it because that's like the data section. And then if you try to manually set the break down below that, it'll do the same thing. So basically, the operating system does what you would expect. It doesn't do silly stuff. That's dangerous. All right. Cool. Let's continue reading. What time is it? Okay, it's 11. Be nice to get through this allocator stuff. Okay. Rather than allocate it in a compiled and fixed size array, malloc will request space from the operating system as needed, since other activities in the program also request space without calling this allocator. The space that malloc manages may not be contiguous. Thus, its free storage is kept as a list of free blocks. Each block contains a size, a pointer to the next block, and the space itself. The blocks are kept in order of increasing storage address, and the last block has address points to the first. So we have the first free list has like some header that's on the left hand side of where it points to the actual data. Oh no, that's not a header, that's other data that's in use. So we have the free list element, it points to the next element, points to the next, points, and then it goes back. In use or owned by malloc as well, okay. When a request is made, the free list is scanned until a big enough block is found. This algorithm is called first fit by contrast with best fit, which looks for the smallest block that will satisfy the request. If the block is exactly the size requested, it is unlinked from the list and returned to the user. If the block is too big, it is split and the proper amount is returned to the user, while the residue remains on the free list. If no big enough block is found, another large chunk is obtained from the operating system and linked to the free list. Freeing also causes a search of the free list to find proper place to insert the block being freed. If the block being freed is adjacent to a free block on the other side, it is coalesced with it into a single bigger block, so storage does not become too fragmented. Determining adjacency is easy because the free list is maintained in order of increasing address. One problem which we allude to in chapter 5 is to ensure that the storage returned by malloc is aligned properly for objects that will be stored in it. Though machines vary, for each machine there is a most restrictive type. If the most restrictive type can be stored at a particular address, all other types may be also. On some machines, the most restricted type is a double. On others, it's int or long suffices. What is this most restrictive type? I don't think that's what they're talking about there, but anyways, let's continue on. So a free block contains a pointer to the next block in the chain, a record of the size of the block, and then the free space itself. The control information at the beginning is called the header. To simplify alignment, all blocks are multiples of the header size, and the header size is aligned properly. This is achieved by a union that contains the desired header structure and an instance of the most restrictive alignment type, which you have arbitrarily made along. Let's try to give ChatGPT some help here. we got char, size 1, alignment 1. Double is more restrictive than int because it requires stricter alignment. K&R mentioned this. Structures char double. Structure must be aligned to the most restrictive member, here double. So struct S alignment is equal to alignment of double. Padding is inserted to satisfy this. Concrete layout AMD64. Yep. Because double is the most restricted type. General. I'm writing a program that needs to know the size of the most restrictive type for how do I discover that at compile time. Max align T. That's C11, which I have. I'm doing C23. Okay, let's do that. So I want to create my header here. So he does it as a union. Of the header pointer. think that should be fine. I don't know why the compiler's complaining. So our S is 16 bytes. Our max align T is 32 bytes. Oh, there's just a line of standard align. Not familiar with that. A line of. I don't get. Well, I feel like I want to grab some lunch here. Been streaming for. I haven't been 2 hours yet. Let me go for 2 hours. Just 9 more minutes here. Screw it. I'm not gonna just push myself. Just for the sake of pushing it. I'm hungry. I'm gonna get some lunch. But we got through that 13 pages of boring nonsense about directories. I mean, we skipped over most of the directory stuff because it's just out of date. But we got over the file IO section as well. And we are now on implementing our own allocator. And what's nice is we can take advantage of all the modern features of C23 to do this. So what my approach is going to be is read their implementation. So they're using a break-based allocator to expand the heap and have a free list that manages the memory that we have in the break. And apparently it's compatible with memory that's not owned by malloc, which is interesting. I'm curious how they're going to keep track of that. I guess the free pointer, the free list? Yeah, because you're going to come back and you're going to ask it to free. It does this interesting trick for alignment. And the header, basically it says, okay, the header, you're going to get allocated blocks the size of the header. We're going to, instead of give you the pointer to the header, we're going to give you a pointer right past the header. And so then it's guaranteed to be aligned if you do this alignment trick. And then we'll just give you, like, say you requested 5 bytes and the alignment is 30 or 16 bytes. We're just going to give you 16 bytes and lie to you and say it's 5. So it's a little bit of wasted memory, but it's properly aligned and it meets the requirement that it's at least as large as the memory that you requested. And when you free it, it doesn't matter, like you're freeing it anyways. So that's an interesting trick. I didn't think of that when I was thinking about allocators recently. And it's using the free list approach. So this is like the traditional approach from what I understand. It's using S break and break. So we'll be extending and collapsing the break instead of just calling mmap, which is interesting. What I might do is like get this in a good state. For this book, and then at a later time when I go and implement like a legit allocator, I'll go through and pull this out into a separate repo, and I'll have multiple allocators implemented. So the break, free list method that they're explaining in the book here will be the first version, and then one that uses like a bump allocator that uses mmap would be like probably the next version. And then if I care to implement more allocators after that, I could have them all in a single repo, just allocators. And the thing that I want to do is I want to be able to replace the test I have for the allocator is like, can I use LD preload to replace glibc's allocator for bash, and see if bash can like just run with my allocator instead of the one that's baked into glibc. So I think that'd be a fun exercise, but yeah, that'll be for future project. That won't be something I do today necessarily. We'll see how far I get on this, but probably not. All right, I'm going to take a break for lunch, and I'll be back in a little over an hour. Cool. All right, see ya.